Hi, my name is Bruce Margatio from the Society of Tribologists and Lubrication Engineers. In the following video, we will speak with Hongyu Gao from the University of California, Merced. He will be talking about his award-winning poster presentation from the 2013 annual meeting titled High Temperature Tribological Properties of Silver Tantalate. Welcome, Hongyu.
My name is Hongyu Gao, and I'm from University of California, Merced. Well, this poster is about the study on the high temperature tribological properties of silver tantalate. For this poster, we try to use molecular dynamic simulations to study the tribological properties of this material and try to understand the underlying sliding mechanism. The setup of this simulation is shown in Figure 2. Basically, we model the contact sliding for two objects. The first is the top rigid plate, and the second one is the substrate triple film. We fix the bottom of the substrate and apply a normal load on the top. Then we drag the plate to slide a certain distance. On the right side, it's a snapshot showing that after we slide a few nanoseconds. We also studied this material in experiment. Figure 3 shows the X-ray diffraction patterns before and after the sliding. On the middle column, the Figure 4a shows the friction force from both the experiment and the MD simulation decrease with temperature and reach to the minimum values at 750 Celsius. We also did the load-dependent test for this material. And in Figure 4b, we can see that the friction force increases with load at both low and high temperatures. Figure 5a shows a TM image from experiment of the cross-section view of a sample during the wear setting test. We can see there's several silver clusters represented by the little dark region and the interfacial region. Well, this phenomenon also captured in our MD simulation. Well, there's a group of silver clusters which circled in yellow, shown in Figure 5b. To correlate these observations to the tribological properties, we try to quantify those silver clusters by dividing the whole triple film into identical cubes with cell length of 0.5 nanometer. Figure 6 shows the number of those high-density cubes increase with the sliding time, which represented by the black circle. And we get a lot more of these kind of high-density cubes at high temperatures. We also measure the average volume for those groups of this high-density cubes. And obviously, the average volume at high temperatures is a little bit larger. On the third column, we also plot the position of the center mass for each layer of our triple film. And we can see the black square shows different starting patterns of the low normal load. We also did the nano indentation test on our substrate, and actually we test on different two substrates actually. One is with perfect crystalline, and the other one is the perfect one sliding a few nanoseconds. So the substrate structure is being changed. Figure 8 shows the reactant forces from those two different substrates and at two different temperatures. To make sure that we get a reliable result from this nano indentation test, we also did the sensitivity test. And we measure different radius of the indenters and different positions where the indenters landed on the substrate. The Figure 9a and b shows the result. Well, to sum up, this poster, we mainly use molecular dynamic simulations to study the topological properties of silver townlake. And we try to understand the sliding mechanism based on what we observed. And we try to have a better understanding of this kind of material. Thanks.
Thank you, Hongyu. If you have any questions about Hongyu's research, you can reach him at hgao2@ucmerced.edu.